Good morning everyone. Good morning everyone. Today I am going to discuss about the grid and cloud computing. So topic is system models for distributed and cloud computing. Okay, system models for distributed and cloud computing. So in this topic we are having some contents, that is cluster of cooperative computers, single system, images, SSI, hardware, software and middleware software, grid computing infrastructures, peer-to-peer network families, cloud computing over the internet. So these are the different topics we are having, contents we are having discussed in these system models for distributed and cloud computing. So coming to the first one, that is, so before going to the contents of that system models for distributed cloud computing, first of all we have know about these system models. So distributed and cloud computing systems are built over a large number of systems. Distributed and cloud computing systems are built over a large number of autonomous computers. So these nodes machines are interconnected by SAN, LAN and WAN. So distributed and cloud computing systems are built over a large number of autonomous computer nodes. So these nodes machines are interconnected by SAN, LAN, WAN. Okay, in this hierarchical manner. So SAN means what? Storage area network, LAN means local area network and WAN means wide area network. So with today's networking technology, a few LAN switches can easily connect hundreds of machines as working cluster. So a few LAN switches can easily connect to the hundreds of machines as working cluster. A WAN can connect many local clusters to form a very large cluster of clusters. So in the sense, one can build a massive system with millions of computers connected to edge networks. So massive systems are considered highly scalable and can reach web scale connectivity either physically or logically. So massive systems are classified into four groups. So first one is cluster P2P networks, computing grids and internet clouds over huge data centers. So the node number, these four system classes may involve hundreds, thousands or even millions of computers as participating nodes. So these machines work collectively, cooperatively and collaboratively at various levels. The table here we have whatever the four system classes in this various technical and application accepts. So this is called the system models for distributed cloud computing. So in these system models, the clusters are most popular in supercomputing applications. In 2009, 417 of the top 500 supercomputers were built with cluster architecture. So we can say that the cluster have laid the necessary foundations for building large scale grids and clouds. So P2P networks appeal most to business applications. So why we are using P2P? For most business applications. The content industry was reluctant to accept P2P technology for lack of copywriting protection in ad hoc networks. So many national grids built in a past decade were underutilized the lack of reliable middleware or well coded applications. So the advantages of this cloud computing includes its low cost and simplicity for both providers and users. So this is the system models for distributed and cloud computing. So next, coming to the clusters of cooperative computers. So a computing cluster consists of interconnected stand-alone computers which work cooperatively as a single integrated computing resources. So in the past, cluster computer systems have demonstrated impressive results in handling heavy workloads with large data sets. So this is the clusters of cooperative computers. So a computing cluster which consists of interconnected standalone computers which work cooperatively as a single integrated computing resources. So in the past, cluster computer systems have demonstrated impressively results in handling heavy workloads with large data centers. So in these clusters of cooperative computer, we having the architecture. This is the cluster architecture. So the architecture of a typical server clusters built around a low latency. Low latency means delay. Low latency, high bandwidth interconnection network. So this network can be simply as a SAN area network, SAN, it is also called, that is Marinate, or a LAN, local area network, that is example Ethernet, to build a large clusters with more nodes. The interconnection network can be built with multiple levels of gigabit Ethernet, Marinate, or InfiniBand switches. So through hierarchical constructing using SAN, LAN and WAN. So one can build scalable clusters with an increasing number of nodes. The cluster is connected to the Ethernet via virtual private network (VPN) gateway. The gateway IP address locates the cluster. The system image of this computer is decided by the way of operating system manages the shared cluster resources. Most clusters have loosely coupled node computers. So all the resources of the server nodes are managed by their own operating system. Most clusters have multiple system images as a result of having many autonomous nodes under different operating system control. So this is the working of this diagram called clusters architecture. So in this we are having single system image, SSI. We can say it is a SSI. So this is the explanation of architecture. Coming to the SSI, single system image. So George Pfister has indicated that an ideal cluster should merge multiple system images into a single system image. So the cluster designers desires a cluster's operating system or some middleware to support SSI, single system image, at various levels, including the sharing of CPUs, memory and input output across all the cluster nodes. So an SSI is a illusion created by software, hardware that presents a collection of resources as one integrated powerful resource. So SSI makes the cluster appear like a single machine to the user. The cluster with multiple system images is nothing but a collection of independent computers. So this is called a single system image. This is called a single system image. So next, coming to hardware, software and middleware support. So in this cluster design principles for both small and large clusters, exploring massive parallelism are commonly known as MPPS. Almost all HP clusters in the top 500 list are also MPPS. The building blocks are computer nodes, that is PCs, workstations, servers or SMPs. Special communication software such as PVM or MPI, PVM and MPI. So and the network interface card in each computer node. Most clusters run under the Linux operating system. The computer nodes are interconnected by a high bandwidth network such as Gigabit Ethernet, Marinate, InfiniBand, etc. The special cluster middleware supports are needed to create SSI or high availability, high availability. So both sequential and parallel applications can run on the cluster, and special parallel environments are needed to facilitate use of the cluster resources. For example, in this distributed memory has multiple images, user may want all the distributed memory to be shared by all the servers by forming distributed shared memory, DSM. Many SSI features are expensive or difficult to achieve at various clusters operational levels. So instead of achieving SSI, many clusters are loosely coupled missions. Using virtualizations, one can build many virtual clusters dynamically upon user demand. So in this virtual cluster for cloud computing, we use this we use this different types of technologies. So this is called the hardware, software and middleware support. So next, coming to major cluster design issues. So the cluster, so in this a cluster wide operating system for complete resource sharing is not available at middleware or operating system extensions were developed. Middleware and operating extensions were developed at the user space to achieve SSI at selected functional levels. Without this middleware, cluster nodes cannot work together effectively to achieve cooperative computing. So the software environments and applications must rely on the middleware to achieve high performance. The cluster benefits comes, we are having some cluster benefits that comes from scalable performance, efficient message passing, high system availability, seamless fault tolerance and cluster wide job management. So these are comes under the cluster. These are the benefits of the clusters. So next, coming to the grid computing infrastructures. So in the past 30 years we have experienced a natural growth path from internet to web and grid computing services. So the internet services such as telnet command enables a local computer to connect to a remote computer. A web services such as HTTP remote access to remote web pages. So grid computing is allow close interaction among applications running on distant computers simultaneously. The Forbes magazine has projected the global growth of the IT based economy from $1 trillion in 2001 and $20 trillion by 2015. So the evaluation from internet and to web and grid services is certainly playing a major role. So in this growth, so we having some features about the grid features. This is the availability and support, hardware fault tolerance, failure management, single system images, efficient communications, cluster wide job management, dynamic load balancing, that is called balancing the workload for all processing nodes, scalability and programmability. So these are the different features we are having in the grid computing infrastructure. Next, coming to computational grids. So in this a grid computing, in this computational grid, a computing grid offers an infrastructures that couples computers, software, middleware, special instruments and people and sensors together. So the grid constructed across LAN, WAN or internet backbone networks at a regional, national or global scale. So the enterprises or organizations presents grid as a integrated computing resources. So they can also virtual platform to support virtual organizations. The computer used in a grid are primarily workstation, servers, clusters and supercomputers. Personal computers, laptops and PDAs can be used to access devices to a grid system. So for example, in the computational grid built over multiple resources sites owned by the different organizations. So in these different organizations, so the resources sites complementary computing resources including workstations, large servers, a mesh of processors and Linux clusters to satisfy a chain of computational needs. So the grid is built across various IP broadband networks including LAN, WANs and already used by enterprises or organizations over the internet. The grid is presented to users as an integrated resources pool as shown in the upper half of the diagram. So the special instruments may be involved, such as using radio telescope in satellite at the rate of home search of life in the galaxy and astrophysics. Okay, so at the server end, the grid is the network. At the client end, we see the wired and wireless terminal devices. The grid integrates the computing, communication, contents, and transactions as rented services. Enterprises and consumers from the user base, which then define the usage trends and servers. So these are called the comes under the computational grid. This is called the computational grid. This is the diagram of the computational grid and data grid. Computational grid and data grid, providing the computing utility, data and information services. So in this we having grid families. So in the grid families, in the grid technology depends a new distributed computing models, software, middleware middleware support, network protocols and hardware instructions. So national grid projects are followed by industrial grid platform development by IBM, Microsoft, Sun, HP, Dell, Cisco, platform computing and others. So new grid computing, new new grid service providers, GSPs, and new grid applications have emerged rapidly. Similarly, the growth of internet and web services in the past 2 decades. So grid systems are classified essentially two categories: computational and data grid. Computational or data grid and P2P grids. So the computing or data grids are built primarily at the national level, and we in this we cover the grid applications and we have learned about this grid applications. So okay, this is the diagram. In this diagram we are having both IP computational grid and data grid. Okay, so next coming to so the grid is built across various IP broadband. The grid is built across various. So this is the grid. So this is the grid. So the grid is in the diagram we are having the grid here. So the grid is built across various IP broadband networks. So if you see the diagram, so we are having the IP broadband network is connected to the grid, and including LAN and WAN already used the enterprises or organizations over the internet. So at the server end, the grid is a network. At the client end, we see a wide or wireless terminal devices. So the grid integrates the computing, communication, content and transactions as rented services. So this is the explanation of this diagram. So next coming to the grid families. So in this grid families, I demands the new distributed computing models, that is software, middleware, support, network protocols and hardware instructions. So in this we use the new grid service providers and new grid applications that are merged rapidly, and similarly the growth of the internet and web services in the past increases in past 2 decades. Next coming to peer-to-peer network families. So for example, a well-established distributed system is the client-server architecture. So in this scenario, the client machines, PCs and workstations are connected to a central servers, for compute, email, file access and database applications. So the P2P architecture offers a distributed model of networked systems. First, a P2P network is client-oriented instead of server-oriented. So in this section, the P2P systems are introduced at the physical level and overlay networks at the logical level. So this is the peer-to-peer network families. In this we are having P2P systems. So in the P2P systems, every node acts as both a client and a server, providing a part of system resources. Peer machines are simply client computers connected to the internet. So all client machines act autonomously to join or leave the systems freely. So this implies that no master-slave relationship exists among the peers. So no central coordination or central database is needed. So in other words, no peer machines has global view of entire P2P system. The system is self-organizing with a distributed control. So in this, if you see the diagram, this is the diagram of the peer-to-peer network. So in this architecture, P2P networks are two abstraction levels. P2P network has two abstraction levels. Initially, the peer are totally unrelated. Each peer machine joins or leaves the P2P network voluntarily. Only the participants peers are from the physical network at any time. So the clusters or grid P2P network does not use the dedicated interconnection network. The physical network is simply an ad hoc network formed at various internet domains randomly using the TCP/IP and NAO protocols. So the physical network varies in size and topology dynamically due to free membership in the P2P network. So we are having over this is the P2P system, peer-to-peer system. Next coming to overlay network. So what is mean by overlay network? So data items or files are distributed in participating peers based on the communication or file sharing needs. The peer IDs from the overlay network at the logical level. The overlay is a virtual network. The overlay is the virtual network. Okay, so in this overlay network, we formed a mapping each physical machine with IDs logically. So a virtual mapping as in the diagram. So a new peer joins the system. So if you want to add a new node or a new computer in this peer-to-peer network, we can add a new computer by adding the peer IDs. So if you want to remove the peer computer or any node from that network, so I will remove the peer ID from the nodes. So automatically it will be overlay networks will be removed. So it is the P2P overlay network that characterizes the logical connectivity among the peers. So there are two types of overlay networks, unstructured and structured. So what is the unstructured and so we having two types of overlay networks, unstructured and structured. So what is mean by unstructured? So in this unstructured overlay network is characterized by random graph. There is no fixed route to send the message or files among the nodes. Floating is applied to send a query to all the nodes in a unstructured overlay. So resulting is heavy network traffic and non-deterministic search results. So what is mean by structural overlay? In the structured overlay networks, follow the certain connectivity topologies and rules for inserting and removing the nodes, that is peer IDs from the overlay graph. Routing mechanisms are developed to take advantages of the structured overlays. So these are the two types we are having in the overlay network. Next coming to P2P application families. So based on application, P2P networks are classified into four groups. The first family is distributed family, distributed file sharing of digital contents like music, videos, etc. on the P2P network. This includes many popular P2P networks such as Guntella, Napster and BitTorrent among others. So collaborations P2P networks include Skype chatting, instant messaging, collaborative design among others. The third family is the distributed P2P computing in specific applications. For example, SETI at the rate of home provides 25 teraflops of distributing computing power collectively over 3 million internet host machines. So other P2P platforms such as JXTA, .NET, Fighting 8 at the rate of home, support naming, discovery, communication, security, and resource aggregation in some P2P applications. So these are things are we are having in the P2P application families. Next, coming to P2P computing challenges. In the P2P computing faces the three types of heterogeneity problems in hardware, software, and network requirements. So there are too many hardware models and architectures to select from. Incompatibility exists between software and the operating systems, and different network connections and protocols make it too complex to apply the real applications. So the system scalability of the as the workload increases, system scalability is directly related to the performance and bandwidth. So P2P networks do not have these properties. So data location is also important that affect the collection of collective performance. Data locality, network proximity, and interoperability are three design objectives in distributed P2P applications. So P2P performance is affected by routing efficiency and self-organization by participating peers, fault tolerance, failure management, and load balancing, and are other important issues in using overlay networks. Lack of trust among peers, another problem. Peers are strangers to one another. Security, privacy, and copywriting violations are major worries by those industry in terms of applying the P2P technologies in business applications. So in the P2P network, all client provides resources including computing power, storage space, input output bandwidth. The distributed nature of the P2P networks also increases the robustness because limited failures do not form a single point of failure. So this is the P2P computing challenges. So next, coming to cloud computing over the internet. So computational science in is changing to be a data intensive. Supercomputers must be balanced systems, not just CPU forms but also petascale input output and networking arrays. In the future, working with large data sets will typically sending the computation programs to the data rather than copying the data to the workstations. So this reflects the trend in IT of moving computing and data from desktops to large data centers. So on the demand of provisioning of software, hardware, and data as a service. So this data explosions has promoted the idea of cloud computing. The cloud computing has defined differently in by many users and designers. For example, IBM is a major player in cloud computing. He defined it as a cloud is a pool of virtualized computer resources. A cloud can host a variety of different workloads including batch style, backbone jobs, and interactive and user facing applications. So these are the different definitions. A cloud allows workloads to be deployed and scaled quickly through rapid provisions of virtual or physical machines. The cloud supports self-recovering, highly scalable programming models, workloads to recover from many unavoidable hardware software failures. So in the cloud systems, cloud should be able to monitor resources used in real time to enable rebalancing of allocations when needed. So this is the cloud computing over the internet. Next, internet clouds. So cloud computing applies a virtualized platform with elastic resources on demand by provisioning hardware, software, and data sets dynamically. The idea is to move desktop computing to a service oriented platform using servers, clusters, and huge databases at data centers. Cloud computing, its low cost and simplicity to benefit both users and providers. Machine virtualization, such cost effectiveness. So cloud computing tends to satisfy many users. So in this internet cloud, the cloud ecosystems must be designed to a secure, trustworthy, and dependable. User thinks of a cloud is a centralized resource pool. Other considers the cloud be a server clusters which practice distributed computing over all the servers used. So in this diagram we are having the user here. We are having in the cloud we are having hardware, storage, service, network, software. These are the different things. The user will be submits the request to the internet cloud in order to access the hardware, storage, services and network and softwares. So sometimes it will be provided the paid service. So it will be provided sometimes free, and sometimes it will be provided the paid of services. So this is the working of the virtualized resources from data centers to form a internet cloud. Next, coming to the cloud landscape. So in a distributed computing system tends to be owned and operated by autonomous administrative domain, that is research laboratory or company, so on the premises of computing needs. So these traditional systems have encountered several performance bottlenecks, constant system maintenance, poor utilizations, and increasing the cost associated with hardware software upgrades. So cloud computing as an demand computing models resolves and relieves us from these problems. So the according to the cloud landscape and major cloud players based on three cloud services models. So one is instruction as a infrastructure as a service, platform as a service, software as a service. So what is meant by infrastructure as a service? So this model puts together infrastructures demanded by users, namely servers, storage, networks and data center fabric. The user can deploy and run the multiple virtual machines running guest operating systems on specific applications. So the user does not manage or control the underlying cloud infrastructures, but can specify when to satisfy. Okay, when to when to request and release the needed resources, that is called infrastructure as a service. Next, platform as a service. So what is mean by platform as a service? So this model in this model the users built applications on the virtualized cloud platform. So PaaS includes middleware, database, development tools and some runtime support such as Web 2.0 and Java. The platform includes both hardware and software integrated with specific programming interfaces. The providers supplies the application programming interface and software tools, that is Java, Python, Web 2.0, .NET. The user is freed from managing the cloud infrastructures. So this is called the platform as a service. Next, coming to software as a service. So it refers browser initialized application software over thousands of paid cloud customers. The SaaS model applies the business processor, industry applications, consumer relationship management, enterprises resource planning, home resources and collaborative applications on the customer side. So there is no upfront investment in the servers or software licensing. On the provider side, costs are rather low compared with conventional hosting of user applications. So this is called the software as a platform. So these are the comes under the cloud landscape. So these are the topics we have discussed in the system models for distributed and cloud computing. So thank you everyone for giving this opportunity. Thank you.